The universe of WebAssembly, because at our research lab at Gent University, what we do is we look at advanced debugging techniques and we build those on top of, or prototypes on top of WebAssembly. And the debugging technique that I'm going to present today is our Multiverse Debugger for I/O applications. And why did we make this debugger? Well, we were looking for I went too fast. We were looking for better debugging tooling for microcontrollers. There have been a few talks at OOPSLA' and also at the WebAssembly workshop that talked about bugs on embedded devices and better debugging tools. So I think we can agree that debugging on embedded devices is hard and we need better tools. And it's especially hard when you're debugging I/O bugs. And I have a small program just to sort of crystallize what exactly is difficult about I/O bugs. This program reads a temperature sensor here, and if it gets too cold, it will turn on a blue warning light, and if it gets too hot, it will turn on a red light, and then if the temperature is just right, both of the LEDs will be turned off. Unfortunately, there's a small mistake in this program, and you will only find it when you have a very specific conditions met. You have to actually lower the temperature to cold enough so that the blue LED turns on, and then when you rise the temperature slowly to the right temperature, then you will actually notice that the blue LED stays on. And so to find this bug, you will have to kind of iterate multiple times over your program until you find the right conditions, and that's not easy. How would we debug this as an IoT developer? Well, usually on hardware. You might not believe me, you might think, I just use a simulator, but actually 74% of surveyed IoT developers in 2021 said that they do debug and test on hardware. And what does that look like? Well, how would you debug our example? Well, there was someone with a similar issue on GitHub. He had his device would get very cold, but some temperature sensor on his device would report 4,000 degrees Celsius. So there was clearly something wrong. And how did they debug that? Well, they used ice packs to cool down the device to sort of replicate this. From the reaction of the room, I think we can agree that this is not ideal. This sounds quite cumbersome if you have to get ice packs out of the freezer. Now, this GitHub issue is from 2017. You might think, surely things have improved. Alas, this is an issue from 2024, last year in November, from the Raspberry Pi Linux repository, and again they're using ice packs to cool down their Pi. So clearly something is missing here. And there's actually a second part of why this is hard. So we don't want to use ice packs, it's hard to kind of get the right input conditions. But on the other hand, it's also often the case that once you see the wrong output, once your bug actually manifests in the output, you're already long past the point in your program where the bug occurred, where the root cause of the bug is. So you kind of want to go back to that point to actually learn something about your bug, but you can't just use reversible debugging, you can't just go backwards because your output won't magically reverse either. And so we also would like to be able to do that. To crystallize all of these problems, just have the three main challenges that we identify in our paper and we address with MIO. And that is, firstly, we want to explore non-deterministic input in programs on microcontrollers. Secondly, we want to have that reversible debugging and keep the output consistent while we do so. And then, of course, we're still in the embedded environment. We want to do all of this on microcontrollers with very few resources. So that's an extra challenge. Now, there's actually room on my slide for a fourth challenge, and we gave ourselves kind of a fourth challenge. We want to do this all formally. We want to have our new debugging technique described formally and have some kind of correctness criteria. I will talk about that at the end of the presentation. I will now start with the first challenge and sort of work my way down. So to explore this non-deterministic input, we looked at multiverse debugging. Now, multiverse debugging is a technique that was first presented at ECOOP 2019, and it's specifically targeted at non-deterministic programs, specifically parallelism in this paper. And the idea behind multiverse debugging is that instead of just debugging one execution path of your program, you're actually going to debug all of the different or many of the different execution paths in your program, so you kind of get this multiverse graph and you can debug all of those at once. Now, The previous works on multiverse debugging were on models, so this is a model of your program. And here, now we want to debug on hardware with I/O, so we want to make that concrete. And specifically, we implement this as a remote debugger on top of our Arduino virtual machine. It's a WebAssembly virtual machine that runs on microcontrollers, these kind of devices. So our debugger just connects to this, and you have a nice front end. This is MIO, a screenshot of MIO. So this runs on your laptop while you actually debug the virtual machine on the microcontroller. And so, because it's an online debugger, a remote debugger, you can step through your program and you will see that you get a nice tree on the right where you can see where in the multiverse you actually are right now, and you can see sort of the history of the inputs that you have explored before. Now, of course, if we want to explore different branches, we don't want to use iSpecs, so we added this mocking feature where we can actually override values of sensor values that we read. So we have our input primitives in the Arduino VM. They return some value from a sensor, but we can actually tell from MIO that ignore that value and just use the one we want. Now, with all of this, we can already go through our multiverse tree, but we want to kind of not always restart our application when we want to explore a new branch. We just want to kind of go back and jump from one place to the other. So that's our second challenge. And what do we need for that? Well, we need our snapshots. And so this is the only part of the formalism I will show you, so don't be scared. We're going to keep it simple. There's only one thing really that you have to remember from our snapshots. They have a KM, that's actually just our WebAssembly state, so that's the state of our WebAssembly program in Arduino, and a compensating action R. And this compensating action R is used to reverse the effects of our output primitives. So with this, we can already in MIO select another branch, like we do here. So we're in the bottom branch and we want to jump to the middle branch. MIO will show you how we will traverse the tree, and then we can just press the jump button on the right and we will go to that place in the program. So this is this figure a bit blown up, so we can, if we have snapshots all along the way, we can go from this node K5 to this node, and so we will go back to the earliest common ancestor that we find, and then we just will replay the execution. And we can of course use our mocking here to replay the input primitives exactly the way we want in this branch, the way our history was recorded before. Okay, so this gives us exploration in multiverse debugging on an actual concrete runtime, and we have this, and our output is consistent, but we're not really doing this efficient yet. So this brings us to our third challenge. Microcontrollers have very few resources. So how do we do this efficiently? Well, we invented a sparse snapshotting strategy where we only snapshot after primitives. So here we have an output primitive, and so after that we will take a snapshot, and then we can just run our program, and then at the next primitive, which is also an output primitive, we will take a snapshot again. So our snapshot list will look a bit like this. We have Kn and Km. And then if we want to take a single step backwards, we simply have to pop our last snapshot off the snapshotting list and perform the compensating action from that snapshot. And then we can restore the WebAssembly state from the previous state. So then we're basically where we were before. In our previous snapshot, our action has been compensated, and we can just replay deterministically the rest of our program up to the point that we need. Why deterministically? Well, we take a snapshot at every primitive, both input and output, so we know there's no snapshots in this path, so there's no input or output primitives. We know that we can just execute the WebAssembly. Now, sort of to test that this actually is efficient, we wanted to check that, okay, taking less snapshots, does that actually have a big impact on the overhead? And when we take less snapshots, we're going to have to replay more instructions. Doesn't that have a negative impact? Doesn't that take too long? So the first thing we measured was we took snapshot at every instruction, and then also at every 5, every 10, every 50, and every 100 instructions. And we see that actually taking snapshot at every instruction is has huge overhead. Here it goes already over 80 times slower than taking no snapshots. It's actually so bad that I kind of have to zoom in to see the other part of my graph. So here you have the different intervals, 5, 10, 50, 100, and then taking no snapshots at the bottom. And so we actually see that this has a huge impact. And the programs that we were usually testing, we would have between 10 and 50 instructions, and in practice it was actually quite fast. You wouldn't notice much delay. And then we also tested, okay, if we have to re-execute more instructions, how much slowdown do we get? And actually we saw that there the impact is very small. We can execute thousands of instructions very fast, and there's actually very little slowdown for our debugger. Now, just really quickly about the formalism, because I have not that much time left. So we had this formalism, I kind of hinted at it already. We wanted to say something about the correctness of it. And we came up with two theorems, debugger soundness and debugger completeness. What is the basic idea is that you have your debugger semantics, and you want those to be, those to not interfere with the language semantics that you're debugging. So if you have a debugging session that starts at the start of your program to some debugging state, this is the first part here at the bottom, then you want to have the same, be able to find the same path in the actual language semantics, so in WebAssembly in this case. And so the reverse of that is the debugger completeness, where if you have a path in your WebAssembly from the start of your program, you want to also have a similar path in your debugger. Now, before I take questions, I just want to quickly say that both my co-authors are also here. They will continue working on multiverse debugging on WebAssembly. So if you have more questions after the session, please go talk to them. They're the perfect people to talk to. And please check out our source code. You can always leave an issue or a star on GitHub. Thank you.
Do we have one quick question for Tom?
Hi, this is Arjun from Carnegie Mellon. I'm wondering, so do you run this code interpreted, compiled?
Interpreted.
It's all interpreted?
Yeah, so the Arduino virtual machine just interprets the WebAssembly bytecode.
Okay. Do you have like any ideas towards like compiled code? Is that like part of like in scope of the Arduino stuff?
So are you talking about JIT compiling or?
Ahead of time probably, because it's on a microcontroller. Right?
No, exactly. So no, we just compile our WebAssembly and just give it to Arduino. You can compile Arduino to several platforms. So you can compile it with Arduino, but also with Zephyr or something. But there's nothing special that we do or any optimization.
Okay, cool. Thanks.
All right. Let's thank Tom one more time.